So in continuation of previous video, there we discussed decoders and how do we implement min term expression using decoders. So in this video we'll explain realization of max term canonical formula. So consider one example, that is implement following expression using 3 to 8 line decoder. The expressions again f1 of 3 variable x2, x1, x0 again and f2. So f1 both are max term expression. For f1 the max terms included is 0, 1, 3, 5, and for f2 1, 3, 6, 7. So how do we implement this using a 3 to 8 line decoder? As you know, 3 to 8 line decoder which we discussed is a min term generator. So convert the max term into min terms. Very simple. Convert the max term into min terms. So f1, if you write a min term expression, so the remaining terms that is 2, 4, 6, 7. Similarly for f2, min term expression is remaining terms, that is 0, 2, 4, 5. So we can implement using output OR gate, and this is the implementation. So to the F1 gate we connected the outputs 2, 4, 6, 7, and to the F2 gate we connected outputs 0, 2, 4, 5. So by converting max term expressions into min term expression and using output OR gate, we can implement a max term canonical formula. Again here either we use a NOR gate or OR gate. So this is the simple table. There it illustrate how do we convert the min term into max term. See, 3 inputs A, B, C. So 8 possible combinations, and randomly we choose an output Y, and Y bar is complement. So if you write expression for Y, the max term expression for output 0, it is 0, 1, 3, 5. So min term expression is summation m of 2, 4, 6, and that is remaining terms. And if you write for a complemented output Y bar, the max term expression is 2, 4, 6, 7, and min term expression is 0, 1, 3, 5. So from this observe max term expressions, the terms included in max term expression of complemented output is equivalent to the terms included in min terms for uncomplemented output. Similarly, min term expression for for a complemented output, min terms included are same as max term expression for uncomplemented output. That means again either we use OR gate or NOR gate, output gate. So we'll consider same example again to illustrate how do we implement using the NOR gate. That means max term canonical expression using NOR gate. So again consider the same example. So first convert the max term expression into min term. How do we convert? See, complemented one. We write complemented one, that is the remaining terms, and its equivalent min term expression is the remaining terms, summation m of 0, 1, 3, 5. Correct? So if you complement on both sides, f1 becomes summation m of 0, 1, 3, 5 whole bar. So similarly for f2, the max term expression is given, and for its complement the max term expression with the remaining terms, and its equivalent min term expression is again remaining terms. So that means same terms which is used in uncomplemented function, that is 1, 3, 6, 7. So if you complement on both sides, so f2 becomes summation m of 1, 3, 6, 7 and whole bar. So the corresponding implementation using NOR gate, that means the same terms 0, 1, 3, 5, it is given in a max term, but the same terms we included for NOR gate. Similarly for F2 gate, the max terms given is 1, 3, 6, 7. So here also same 1, 3, 6, 7 is connected to NOR gate. So max term expression can also be implemented using decoder again, either using output OR gate or using output NOR gate. Clear, no? So we came to know that we can implement both min term expression and max term expression. Now we'll see NAND gate decoder. NAND gate decoder. So previous one which we discussed is called as AND gate decoder. Why? Because for circuit diagram we use AND gates. So here one more decoder, that is NAND gate decoder. It is frequently used. Okay, that means n to 2 to the power line decoder are constructed from the NAND gate. There it is constructed from the AND gate. So if we use NAND gates, outputs are active low. See the truth table. Again consider the example 3 to 8 line decoder using NAND gates, and the corresponding truth table is, observe the truth table. Okay, again inputs are x2, x1, x0, and outputs are z0 dash, z1 dash, z up to z7 dash. That means outputs are active low. Either we represent as a bar, z0 bar, z1 bar, or z0 dash, z1 dash, like that. And again, so since there are 3 inputs, 8 possible combination. Observe for first combination, for that is 3 zeros, z0 is 0, remaining are 1. Z0 is 0, remaining are 1. That means Z0 is selected. So here outputs are active low. As you know, active low means 0 means selected, 1 means not selected. So in the previous AND gate decode, it was 1, the remaining are 0. So those outputs are called as active I outputs. So there we use the symbol Z0 to Z7. They are active I outputs. Here we use the symbol Z0 dash to Z7 dash. That is complemented output. In the complemented output, 0 means selected, 1 means not selected. So observe similarly second combination, that is 0, 0, 1. Z1 dash is 0, remaining are 1. So Z1 is selected. The remaining are not selected. Similarly for the combination 1, 0, 1, that is 5. So Z5 dash is selected, 0. The remaining are 1. So remember, NAND gate decoders are active low output decoder, and AND gate decoders are active I decoder, active I output decoder. So here only one output is a 0, the remaining are 1. So output is logic 0 for only one input combination. Okay, and let's see the logic symbol. Observe the logic symbol. Again here inputs are 0, 1, 2. To the 0, 1, 2, x0, x1, x2 is connected. Outputs are 0 to 7. So here in the output we use a bubble. That is complemented. Outputs are complemented. Active low outputs are all complemented. They are represented by a bubble. So Z0 dash, Z1 dash. As we know in the previous, Z0 expression is x2 bar, x1 bar, x0 bar. So because of this output bubble, we do whole complement. And if you apply De Morgan's law, it becomes x2 plus x1 plus x0, and that is corresponding to max term. Otherwise, see from the truth table, observe z dash 0 column. So only one output is 0, the remaining are 1. So if you write some expression for output 0, we write the sum expression for output 0. Okay, so the corresponding input combination is 3 zeros. So here if it is 0 means uncomplemented. That is why we write x2 plus x1 plus x0. Otherwise, from the logic symbol, since the outputs are complemented, we do whole complement and we apply De Morgan's law. Okay, similarly see Z3 dash. So in the previous we got an expression x2 bar, x1, x0. Because of this output bubble, whole bar, and applying De Morgan's theorem, it becomes x2 plus x1 bar plus x0 bar, and that is corresponding to max term M3. So we call NAND gate decoders are max term generator. So here we use NAND gate. See, this is the corresponding circuit diagram. Here we use a NAND gate. We use a NAND gate. Inputs are same. So for first one Z0, inputs are x2 bar, x1 bar, x0 bar. Because of NAND gate, it is whole bar, and if you apply De Morgan's law, it becomes max term. Okay. So from the circuit diagram, we can see each output is described by a single max term. Hence, NAND gate decoder is also called as max term generator. So, NAND gate decoder along with the AND gate realizes the max term canonical form of Boolean functions. Right? So, we'll consider an example. So realize the following pair of Boolean expression f1 and f2 of three variable x2, x1, x0, and the given expressions are max term expression 0, 2, 0, 3, 5 for f1 and 2, 3, 4 for f2. And this is the corresponding implementation. So to collect the max term, we use AND gate. Correct? Max term is product of sums. So for performing product, we use AND gate. To the F1 AND gate, we connect the max terms 3, 0, 3, 5. So output 0, 3, 5 is connected. Similarly, for F2 AND gate, the max terms included is 2, 3, 4. So here output 2, 3, 4 are corresponding to the max term 2, 3, 4. So they are connected as an input to the F2 AND gate. Okay, similarly here, as we analyzed it in AND gate decoder for implementing a min-term expression, when more than one of total possible max terms occur in the Boolean expression, it is convenient to use NAND gate instead of AND gate. So output AND gate can be replaced by a NAND gate to reduce the number of inputs. Let's consider one example. Yeah. So realize the following pair of expressions f1 and f2 of max terms. For f1 1 3 0 1 3 4 7, and for f2 1 2 3 4 5 6 7. So both are more than half. For 3 variable 8 possible max terms are there, so they are more than 1/2. So again perform right output, complemented output. So here f1 is max term of 0 1 3 4 7, and its complement f1 bar is the remaining terms, that is 2 5 6. Again complement on both sides, it becomes f1 is equal to complement of f1 is equal to summation pi m of 2 5 6 and whole complement. Similarly f2 and its complement max term expression is 0 7. If you perform complement on both sides, f2 becomes f2 is equal to pi m of 0 7 and whole bar. So again, so for max term we use AND gate, because of whole complement we use NAND gate. Observe the implementation. For f1 NAND gate, we connected the outputs of 2 5 6. 2 5 6, and again similarly for f2 gate we connected the outputs of 0 and 7. So this is how we use either AND gate or a NAND gate along with the NAND gate decoder to implement the max term expression. So max term generator can also be used to realize the min term. That means to say, so we observe that NAND gate decoders are max term generator. So along with the NAND gate decoder and either AND gate or NAND gate, we can implement a max term expression. So this can also be used to realize the min term expression, as we used AND gate decoder to implement the max term expression. We can use a AND gate decoder, that is max term generator, to implement the min term expression. Again, either using AND gate or NAND gate to collect the max term. So let's consider one example. Okay. So realize the following expression. The following given expressions are minterm expression of three variable. For F1, the minterms are 2, 0, 2, 6, 7. For F2, the minterms are 3, 5, 6, 7. So convert this into max term using AND gate. Convert this into max term. So the remaining terms are included for the max term. So F1, for F1, the max term expression is 1, 3, 4, 5. Similarly, for F2, the remaining terms 0, 1, 2, 4. So we use NAND gate decoder and AND gate. And gate. This is what the corresponding implementation. Okay. So we can also use NAND gate. Output NAND gate. One second. Yeah. So consider the same example. Let's illustrate how do we use a NAND gate. Using NAND gate. Yeah, using NAND gate. So first write complemented output. So F1 is the max terms included are 1, 3, 4, 5. And for complemented output, again max term means a remaining terms, that is 0, 2, 6, 7. So again, if you complement on both sides, F1 is equal to pi m of 0, 2, 6, 7 and whole complemented. Similarly, F2 and write F2 bar max term expression, and if you complement on both sides, F2 is equal to pi m of 3, 5, 6, 7 whole bar. So because of 4 complement, we use a NAND gate. We use a NAND gate. Clear now? Yeah. So we can use NAND gate decoder to implement the minterm expression as well as max term expression, but we should convert accordingly based on either we use output AND gate or output NAND gate. So in the next video we'll discuss a decoder with enable input.